Hi, I'm Swapnil and my talk is about training graph neural networks at scale. This is a joint work with Anand Iyer from Microsoft Research. Graph neural networks are an increasingly popular deep learning method targeted towards graph structured data and is shown to achieve remarkable performance across a wide range of domains such as sciences, computer vision, natural language processing, and search and recommendation. GNNs use neural message passing scheme to combine two things. First, they use the structure of the graph to determine what information to propagate. For example, here the two-hop neighborhood of node A determines what information it eventually receives in form of messages. Second, neural networks determine how neighborhood information is transformed. At each hop, nodes use neural networks to aggregate and transform information propagated from their immediate neighbors, and as this information iterates, nodes incrementally gain more and more information from further reaches of the graph. Together, they allow the GNN model to eventually generate representations that capture useful node feature as well as structural information. GNN models are typically organized as a stack of two or more layers, and within a layer, same neural network and weight parameters are used to aggregate and transform messages. Increasing popularity of graph neural networks are driving two main trends. First, the inputs used for training GNNs are becoming larger. It is now common to find graphs with millions of nodes and billions of edges. Second, GNN model architecture are becoming richer and more complex. This increase in input size and model complexity makes distributed training of GNNs very common. Today, frameworks that support distributed training of GNN combine distributed graph processing techniques with techniques designed for distributed training of neural networks. Specifically, they use distributed graph processing techniques to store a large input graph across multiple machines. A partitioner is used to cut the input graph into several disjoint subgraphs. Each machine holds one such subgraph and node features for local nodes. Graph processing literature consists of many partitioning schemes. Some optimize computation while others optimize communication. For distributed training, existing GNN frameworks leverage data parallelism, a widely used technique to scale out model training across several machines. Here, input dataset is divided equally among all machines. At the beginning of a training iteration, each machine randomly selects data samples to form a mini batch. Next, it completes a forward and a backward pass over local copy of model being trained, synchronizes gradients using collective communication, and applies weight updates to its local model copy. Post that, it moves to next iteration. Putting things together, GNN frameworks first partition the graph structure and features using existing graph partitioning schemes. Each machine must create the computational graph for every node in its mini batch. Doing so requires access to its k-hop neighborhood. Because input graph is partitioned, it is commonly the case that no single machine contains a node's k-hop neighborhood. Therefore, each machine must communicate with one or more machines and pull neighborhood information and associated node features over network. Once these computational graphs are generated, machines collectively participate in model training. During the forward pass, layers in GNN combine node features and structural information to generate node embeddings. During backward pass, loss is propagated through all layers and computed gradients are synchronized before updating local weight parameters. Training GNNs in this manner results in two main scalability challenges. First, we have found that the network communication overhead shown by the filled portion in this plot dominates the training time for different GNN architectures and datasets and leads to underutilization of GPUs, sometimes as much as 80% of the time. Second, computationally simple partitioning schemes do not yield intended performance uplift. Partitioning schemes which are effective are also computationally expensive, and even they provide diminishing returns as the number of layers increase. In this work, we introduce pcube, a system that addresses these issues by proposing a new push-pull based technique for distributed GNN training. PQ builds on two key observations. First, we notice that movement of features causes majority of network overhead. Graph structure on the other hand is compact. Thus, in PQ, we opt to avoid movement of features altogether. Second, existing GNN frameworks consider graph structure and associated features as indivisible and partition them as a single entity. In PQ, we consider them as two separate entities and opt to partition them independently. Together, these design choices result in faster training time across a range of GNN architectures. Graph structure in PQ is partitioned using a computationally simple and low overhead random hash partitioner. Independently, node features are partitioned along columns and are spread across machines evenly. Therefore, like existing GNN frameworks, each machine in PQ stores a disjoint subgraph. However, unlike existing frameworks, each machine only stores partial features, but for all nodes, irrespective of the subgraph it is assigned to. During generation of computational graph, like existing GNN frameworks, PQ must communicate with one or more machines and pull neighborhood information over network. However, unlike existing GNN frameworks, PQ never moves features over network. Recall that majority of network traffic can be attributed to feature movement, and thus this design choice results in reduced data communication. However, this introduces a new challenge. Existing systems have both computation graph and node features available locally and therefore can train GNN model using data parallelism. However, PQ's design choice to skip movement of features entails that computation graph and only partial node features are available locally. Thus, PQ cannot make use of data parallelism. While using model parallelism, a commonly used alternative to data parallelism, is an option, it does not yield tangible performance improvement due to frequent synchronization overhead. Instead, in PQ, we use a hybrid of data and model parallelism for distributed training. In this hybrid model, each machine first creates the computation graph for every node in its mini batch. This requires communication with other machines. Once this is complete, PQ pushes the generated computational graph to all machines. Notice how computational graph in PQ only consists of structural information and is therefore compact. In the end, each machine holds generated computational graph and slices of feature vectors. Next, PQ starts the forward pass in a model parallel fashion. Here, each machine computes partial activations for layer 1 using the slice of partial input features it holds locally. Once the partial activations are computed, each machine pulls partial activations from all machines and aggregates them using a reduce operation. Moving intermediate activations instead of features is a worthwhile trade-off because hidden dimensions used in GNNs are typically small and thereby the intermediate activations and gradients are small as well. Here, x-axis shows different GNN models and datasets and y-axis shows communication overhead of moving features versus activations. By opting to synchronize activations, the overhead drops from 80% to just 20%, and as we show through evaluation, this results in faster epochs. Once intermediate activations are synchronized, PQ switches to data parallelism, and for all subsequent layers, computation proceeds in a data parallel fashion. Once node embeddings are generated and loss computed, the backward pass also proceeds in a data parallel fashion, invoking global gradient synchronization until it reaches layer 1. At this point, PQ pushes computed error gradients to all machines and switches back to model parallelism. Backward pass over remaining operators of layer 1 is performed using model parallelism and gradients synchronized locally. Finally, iteration ends with local weight update. Though hybrid parallelism avoids movement of features and thereby reduces data communicated, its use of model parallelism introduces need for activation and gradient synchronization. This newly introduced communication during forward and backward pass results in computation stall, which negatively impacts resource utilization and training throughput in PQ. To limit such stalls, we leverage a static pipeline schedule. P-cube schedules 3 concurrent mini batches, and once pipeline enters steady state, this ensures computation and communication overlap. The use of pipelining improves P-cube's performance by up to 50%. By partitioning graph structure and features independently, P-cube opens new opportunity to selectively cache graph structure and or features on multiple machines. Let's assume we have an input graph for which graph structure fits in a DRAM of a single machine, but coupled with features, it does not. Instead of partitioning and spreading out the graph structure and associated features across machines, P-cube supports caching the structure while only partitioning features. Doing so improves training throughput by up to 1.7x, as in addition to features, P-cube now also avoids movement of graph structure. Finally, P-cube wraps its independent partitioning strategy, pipeline push-pull parallelism, and caching in a simple API, which users can leverage to speed up existing and new GNN architectures. More details about it can be found in the paper. We have prototyped P-cube on Deep Graph Library, a popular open source GNN framework which supports distributed training, and have evaluated it on a small cluster of 16 NVIDIA P100 GPUs. We used several openly available graphs which with varying structure and feature size, and with a variety of GNN architectures. In the next few minutes, I will provide an overview of some of the results that show the efficacy of P-cube's design choices. First, we show the performance of P-cube on different GNN architectures and input graphs. The x-axis shows the input graphs ordered by size, so as we go to the right, the size of the graph increases. X-axis also shows the GNN architectures used in this experiment. The y-axis shows the epoch time in seconds, averaged over several runs. We see that compared to P-cube, DGL takes more time per epoch, and that the performance gap widens as graph size increases. P-cube's up to 7x speed up compared to DGL can be attributed to reduced network overhead. The second result shows the scaling characteristic of P-cube as the size of input features grow. The x-axis here shows the feature size and y-axis shows the epoch time in seconds. As we see, DGL exhibits poor scaling characteristic as the feature size increases. Recall that existing frameworks for training GNN, including DGL, move features over network. Therefore, any increase in feature size directly results in increased network communication. Instead, P-cube scales gracefully. While these results are encouraging, we would like to note that there is no free lunch. Here, x-axis shows the hidden dimension size and y-axis shows the epoch time in seconds. A fundamental assumption P-cube makes is that hidden dimensions in GNNs and thereby intermediate activations are small and can be traded off for feature movement. When this assumption is invalidated, in this case as we move from left to right, P-cube provides little to no benefit and in some cases may even perform worse. In addition to the presented results, we also study the impact of various partitioning strategies, effect of neighborhood sampling, and much more. Details about them can be found in the paper. To summarize, distributed training of graph neural networks is increasingly important as the graph size increases and new and more complex GNN architectures emerge. Existing frameworks combine graph partitioning with data parallelism. This results in high network communication and partitioning overhead. We have built P-cube, a system for distributed GNN training that eliminates these overheads and achieves significant performance gains. That brings me to the end of my talk. Thanks for listening.